Hi, welcome to this video of me completing a 2014 AQA Physics P2 GCSE paper. Okay, I'm going to go through all the questions on this paper and just go through the logic in how I'm answering them. So we start with question 1. We've got a slide in a children's playground and a picture of that in case you didn't know what a slide in a children's playground looked like. So we're given a calculation question to start with. A child of mass 18 kilograms goes down the slide. The vertical distance from the top to the bottom of the slide is 2.5 meters. Calculate the decreasing gravitational potential energy for the child sliding from the top to the bottom if the gravitational field strength is 10 newtons per kilogram. So you've noticed that I've just circled those key values because we're going to need those in a minute. So it tells me to use the correct equation from the physics equation sheet. So I look that up and I find that GPE is equal to m for mass times g for gravitational field strength times h for height. So 18 times 10 times 2.5. So I pop that into my calculator. Okay, so 18 times 10 times 2.5 gives us 450 joules. Okay, nice and simple. The slide is made of plastic. The child becomes electrically charged when he goes down the slide. Explain why. Okay, so when things become electrically charged, it's because two surfaces have rubbed together and friction has caused transfer of electrons. So we need to say what two surfaces there's friction before. There is friction between the child and the slide. This causes electrons to be transferred. We're not expected to know whether they're transferred from child to slide or slide to child, and if you write either of those, then either one is absolutely fine. Okay, going down the slide causes the child's hair to stand on end. What conclusion can we make about the charge on the child's hair from this observation? So, if this hair's standing on end, it must be repelling from the other hairs. So we know that repulsion happens when it's got the same charge, so we can say all the charge is the same. And how we knew that? The hair repels. Okay, why would the child not become electrically charged if the slide was made from metal? Well, that's because metal is a good conductor of electricity. So the charge wouldn't get built up, it would just be conducted away. Okay, question 2. Stars go through a life cycle. Some of them will finish their life cycle as black dwarf and others a black hole. So the first thing I know is that black dwarf is going to be small. The word dwarf is usually a pretty good clue for that one. And black holes come from large stars. So we have to be careful here about whether we're thinking about black dwarfs or black holes. We've got the mass relative to the sun, so this is how many times the sun's mass these three stars are, J, K and L. Which one is going to become a black dwarf? Well, we know that black dwarfs come from small stars, so we're going to pick the smallest one. It's going to be J. It is the smallest. Okay. Scientists take measurements needed to calculate the mass of many stars. They can't calculate the mass of the star Betelgeuse. They estimate that it has a mass between 8 and 20 times the mass of the sun. So we're looking at a big star. It is in the red supergiant phase of its life cycle. What will happen to Betelgeuse at the end of the red supergiant stage? So this is about knowing your stellar life cycle. It will turn into a supernova, which is of course the explosion of a star. Okay, one reason why scientists can only estimate and not calculate the mass of Betelgeuse. They love questions, why, especially with relation to space, why do we not know this thing yet? It's because we don't have the technology. Technology isn't good enough. Okay, so in the future it might become possible for scientists to calculate the mass of Betelgeuse. Why? Well, we said technology isn't good enough yet. Technology could improve. Yep, it's stating the obvious. Okay, describe what happens to a star after the main sequence period for it to eventually become a black dwarf. So we're back to looking at small stars because we're looking at a dwarf. Okay, so after the main sequence period, the star becomes a red giant. And in becoming a red giant, it is expanded by expanding. So we've got 2 marks there. Eventually it loses its outer layers. And shrinks because it's lost its outer layers. And what's left behind is a white dwarf. So we've got 4 points there. It expands, it becomes a red giant. It shrinks, it becomes a white dwarf. This then gets cooler and dimmer. To become a black dwarf. Now it's really important when you've got questions like this that you don't talk about things that are on the other path of the life cycle. So if we're looking at small stars, if you mention supernovas, black holes, neutron stars, you're going to lose marks for that. So you've got to make sure that you are looking at the right half of the star life cycle. Okay, moving on. It's a bicycle. It's horizontal forces acting on a moving bicycle and cyclist. What causes force A? So force A is acting horizontally, it's acting between the wheel and the road. That means it's got to be friction. Okay, so what causes force B? That's acting backwards on the rider, so it's going to be air resistance. Okay, and now we've got our 6 marker. In this question, you will be assessed on using good English, organising information clearly, and using specialist terms where appropriate. So we want to make sure that our answer to this is really logical. Figure 3 shows how the velocity of a cyclist changes during the first part of the journey along a straight and level road. During this part of the journey, the force applied by the cyclist to the bicycle pedals is constant. So we've got constant forward force. Now let's just look at how this velocity is changing. In between X and Y, the velocity is increasing. That means the bicycle is accelerating. But it's increasing at a slower pace the further you go. So it's increasing a lot at first and it's increasing less towards the end. Between Y and Z it starts to flatten out, so we're getting a constant velocity, so no more acceleration. Okay, describe and explain in terms of the forces A and B. So we want to be using ideas about forces, why the velocity of the cyclist changes between these points. Now we've already been told here that the force applied to the pedals is constant, so the forward force, A, is constant. Okay, so between X and Y then. We've already said that the velocity increases, so we'll put that down. The bike is accelerating. try not to go over the edge of the box like I've just done, because when they scan your answers to get sent off to the markers, often it loses the bits that have gone outside the box. Okay, so the bike is accelerating. This is because force A is bigger than force B. Now, we've already said that the acceleration was going to get less as it goes on. And the reason for that is because force B increases when the bike gets faster. As the bike gets faster, force B increases. So the acceleration gets less. So what's happening between Y and Z? Between Y and Z, force B becomes the same size as force A. The resultant force, remember we're looking for specialist terms, becomes 0. So there's no acceleration. The bike's reached terminal velocity. Okay. And see, I don't need to use this extra space at all. You should only really be going into the extra space bit if you've got big handwriting. Okay, cyclists use brakes to slow down and stop the bicycle. They've applied a constant braking force of 140 newtons to stop the bicycle in a distance of 24 meters. So again, let's highlight those two values. Calculate the work done by the braking force to stop the bicycle. Give the unit. I'm going to circle that as well because I don't want to forget to give the unit. That's always worth a mark if they've said it in the question. Okay, so what's the correct equation? Work done is equal to force times distance. So 140 times 24. Again, pop that in my calculator, which gives me 3,360. And work done is a type of energy, so that's going to be measured in joules. When the brakes are used, the bicycle slows down. The kinetic energy of the bicycle, it's slowing down, so it's moving less, the kinetic energy decreases. At the same time, the something of the brakes increases. So we're losing kinetic energy. If we think about it, the energy that's turning into is going to be heat energy. So the temperature of the brakes is going to increase. Okay, 4A, whoa, electricity question. Here's a circuit diagram showing the data. The apparatus needed to get the data to calculate the resistance of a thermistor at different temperatures. Okay, so we're given some data in there, which I'm sure we'll need later. So the current, we've got a voltage, and we're showing that that's at 20 degrees C. So the first thing they've asked us to do is draw the circuit symbol for a thermistor. Okay, you've just got to learn your circuit symbols. The thermistor is the one that's the rectangle because it's a type of resistor with a hockey stick through it. Okay, use the data given to calculate the resistance of the thermistor at 20 degrees. Well, we know that these readings were taken at 20 degrees. So we can use the equation V equals IR, and we need to rearrange that one. So we want to get I onto that side. So to do that, we're going to divide R equals V divided by I. V is the voltage, I is the current, obviously. So our voltage was 9. We're dividing that by 0.025. We just check that that's in amps and volts and not milliamps or anything that's trying to confuse us. Okay, again, go to the calculator. 9 divided by 0.025 equals 360. It then asks us to draw a sketch graph for how the resistance of a thermistor changes as the temperature increases. So as the temperature increases, you should know that the resistance decreases, and it doesn't do that in a linear way. Curve. Okay, which circuit is most likely to include a thermistor? Plant watering? Nah. Outside light on when it gets dark? Nah. Heating system. Thermistors to do with temperature, it's going to be the heating system. The ammeter used in the circuit has a very low resistance. Why is it important that ammeters have very low resistance? That is because we want the current to stay at the same level. If it has a high resistance, it's going to affect the current. So it doesn't affect the current. Because what's the point if you change the current and then your reading will be wrong? Okay, here is the temperature of boiling water using 3 different temperature scales: Celsius, Fahrenheit, and Réaumur. Why do scientists in different countries use the same temperature scale to measure temperature? What's the advantage of doing this? So they can compare their results accurately. Okay, a student plans to investigate how the resistance of an LDR changes with light intensity. Student starts with the apparatus shown in figure 4, but makes 3 changes to the apparatus. 1 is to replace the thermistor with the LDR. What other changes should they make? So we don't need anything to heat it with, so remove beaker of water and Bunsen burner. Replace with what we are going to need. An LDR is a light dependent resistor. They've told us that. So it's something that's going to depend on the light. So we're going to want a light source, a lamp. Okay, and then the other thing we're going to need to change on here, we were using a thermometer to check the existing temperature. We're not going to need that anymore. So we can remove thermometer and replace with a light sensor or light meter. Okay, figure 6 shows a skateboarder jumping forwards off his skateboarder. The skateboard is stationary, so not moving at the moment the skateboarder jumps. That's going to be really important. The skateboarder moves backwards as the skateboard moves backwards as the skateboarder jumps forwards. Explain using the idea of momentum why the skateboard moves backwards. So we're using the idea of momentum. We don't care about equal and opposite forces at this point. So what do we want to say? We want to say that before the skateboarder jumped, the momentum was 0. We know that because it's not moving. Before the skateboarder jumped, the total momentum was 0. As a result of that, because of conservation of momentum, the momentum before has to be equal to the momentum after. Momentum before jump is equal to momentum after. So the total momentum after has to be 0. that means that the forward momentum of the skateboarder has to be equal to the backwards momentum of the skateboard. Okay. So we're going to use that now. The mass of the skateboarder is 1.8 kilograms and the mass of the skateboarder is 42 kilograms. Work out the velocity of the skateboard if the skateboarder jumps forward with 0.3 meters per second. So momentum forwards is equal to momentum backwards. Okay, so the momentum forwards is mass times velocity, so 42 times 0.3. And the momentum backwards, again, mass times velocity, is 1.8 times our mystery value. So if we do 42 times 0.3 divided by 1.8, that will give us our velocity. 42 times 0.3 divided by 1.8 gives us 7. Okay, there are many isotopes of the element molybdenum. What do the nuclei of different molybdenum isotopes have in common? So, it's an element. All elements have the same number of protons. You can't say same number of electrons, even though it might be true, because they ask you about the nucleus, not the atom. The isotope of molybdenum-99 is produced inside some nuclear power stations from the nuclear fission of uranium-235. What happens during the process of nuclear fission? The isotope molybdenum-99 is produced inside some nuclear power stations from the nuclear fission of uranium-235. What happens during the process of nuclear fission? The nucleus of, actually, change that. I'm going to say heavy nuclei, that's one with the big number there, split into smaller nuclei. And also important that you're using nucleus or nuclei, not talking about atoms. Okay, inside which part of a nuclear power station would the molybdenum be produced? That would be in the reactor, not the staff toilets. So, when the nucleus of molybdenum-99 decays, it emits radiation and changes into a nucleus of technetium-99. What type of radiation is emitted? Okay, so if we look at this, we've got the same mass number. That tells me instantly that it must be beta decay. And I'm confirming that by seeing that the proton number is different. Okay, that's because in beta decay, a neutron turns into a proton. So the proton number's gone up by 1, but the overall mass has stayed the same. Okay. Technetium-99 has a short half-life and emits gamma radiation. What is meant by the term half-life? That is the time taken for the number of radioactive nuclei to half. Okay, and we've got a half-life graph here. Okay, so we're given some information about it being used as a medical tracer in hospitals, and it being produced by molybdenum-99 decay. And then here is a graph showing how the number of molybdenum change with time as the nuclei decay. Technetium generator will continue to produce sufficient technetium-99 until 80% of the original sample have decayed. After how many days will a source of molybdenum-99 need replacing? Okay, so we're starting out with 100,000. So 100,000, we want 80% of it is going to be 80,000. So that gives us 80,000. So we're looking for when there is 20,000 left. So we're going to go back to our graph, go across at 20,000 and down very carefully, obviously, following the line there. And that's gone to one small box. There are 5 small boxes between divisions, so that's going to be 6.2 days. Okay, medical tracers are injected into a patient's body. This involves some risk to the patient's health. Explain the risk of using a radioactive substance as a medical tracer. Okay, so radioactive substances are ionizing. That means that they can damage cells and they can damage DNA. Just make that a little bit clearer. Even though there may be a risk, doctors frequently use a radioactive substance for medical diagnosis and treatment. Suggest why. The risk is low compared to the benefits. Okay, we've got an electric drill. Lots of information here. Plastic grips, plastic handles, plastic covers, 2-core cable. And we've got some information about the power supply, power input and mass. Why is it safe for the drill to be fitted with a 2-core cable rather than a 3-core cable? Plastic grip, plastic cover, plastic handle. That's all insulators. It is what we call double insulated. That's all you need to say. Okay, then it wants us to work out the power. So we need an equation. The equation we want is power equals current times voltage, PIV. We want to find current, so we need to rearrange. So I is equal to P over V. We know that P is 1012. We know that V is 230. We pop that into our calculator. Which gives us 4.4 amps. It's advisable to use 230 power tools with a residual circuit current breaker. How does a RCCB operate? It detects a change, well, no, it detects a difference in current between the live and neutral wires. And there's your favourite, should be your favourite part of where you get to the end of questions. We are done. Of course, you go back and check through your answers at this point if you've still got any time left. Thank you for watching, and I hope this has been useful.